So, root locus and frequency domain design techniques, which is what we've learned so far, those two techniques. They have their own strengths, but they can't be applied to a broad class of systems, including nonlinear systems and multiple input, multiple output systems. So everything we've done so far has been for single input, single output systems. I don't know if you've noticed that, but definitely the case. And so we learned to model multiple input, multiple output systems. State space, you could do any number of inputs, any number of outputs. So modern control theory was developed to tackle that problem. Like, what do you do when you've got multiple inputs, multiple outputs? What do you do when you have a nonlinear system? What do you do with more complex modern systems that we deal with? And we're barely going to brush the surface of this, but I'm going to at least give you a little bit of an introduction to it, and it'll give you a feel for where we go from here in controls. Moreover, these techniques, meaning the classical techniques, can only attempt to specify the locations of the dominant closed-loop poles. Therefore, those systems for which higher order poles significantly affect the response do not respond well to these techniques. So you are using the second order approximation always when you're using those classical techniques for design. Almost always that's what we're thinking in terms of is second order approximation. If we move the poles to the left, we're talking about settling time, decreasing, and all that. But it's always based on there being only two dominant poles. But there are a lot of systems, well, I wouldn't say that they come up frequently, but they come up frequently enough that don't follow those sorts of behaviors. And so you have to be able to have some design techniques that can get around that type of thing, built for those types of systems. These are some of the reasons why modern control theory uses state space design techniques. Drawbacks of these techniques are limited, but include that less insight can be gained from them, and that closed-loop zeros can't be specified directly, which you can do in some ways of designing the root locus. Now, another drawback, which I didn't mention, is that these design techniques are more complicated, they're more complex, and so not only do you lack intuition sometimes, but you also lack sometimes the ability to wade through the complexity of the design without making a mistake. So there are these tools that we'll learn about, like in MATLAB, that help us a lot with this. So we're gonna build our own controller using MATLAB to do some basic operations, but actually MATLAB has built into it this nice function that can do all of what we're going to do in like one swoop.
Yes. Are you going to upload some sample code?
Yeah, I will. I forgot to do that earlier, but I will. So I'm going to do an example in class, and and I will definitely post that code because it is helpful to see the code. And MATLAB has a function that does essentially this to, it's called Acker, A-C-K-E-R, but you could use it but not have any idea of what it means. It's the same, you can do optimal control theory with MATLAB too. LQR is a function in MATLAB you can do. So, yeah, I mean, MATLAB, it can be used as a black box to do some controller design. It's not necessarily bad. But it's dangerous. Like, it's dangerous to use something if you don't understand what it means at all. So I definitely discourage that. For an nth order plant, n poles must be placed for this type of controller design. So if you have an nth order plant, we're going to place all of them where we want. So we're just going to say, oh, you have 5 poles. These are where the closed loop ones we want them to be, which is nice. This requires n adjustable parameters, which are all going to be gains. We're going to have n gains in our controller. So instead of having like PID gains, like 3 gains to adjust, we're going to have n, the number of the system order. So if it's a 4th order system, we'll have 4 gains to adjust. We won't do much of any of that by hand, however. It will be done automatically to place those poles in certain locations. So that's what we're doing. Note that in the following, I don't have a lot of discussion of the control effort that goes into this. But that is a key, as the controls group in simulation has discovered. And you can say you're going to have a controller that has these gains or whatever, and that's great. But if your controller can't supply that much power, then it doesn't matter if your theory says that that's the right controller for you. The real system's not going to respond like that. So keep that in mind when we do this design, that you might be able to say this is where I want my poles to be, but if you really want your poles to be there, then you're going to have a system that can provide power. Yeah.
I don't want to go off too much of a tangent, but is there a way to build in those power limits to your model?
Yes. And the way to do it is actually not to use like LSIM or anything like that to simulate your system. The way to do it is to take your state model and construct a function file to plug into ODE45. And ODE45 is just a solver, an ODE solver. But your state space model is already in the right form for the LSIM or for the ODE45 or other ODE solver. So it's pretty easy. Like you can just put like AX plus BU in the function file. But then in that function file, at every time step, you can limit your input. And so you can essentially you can open it up and tweak with the things at every time step of the simulation. Whereas you can't do that in LSIM; it doesn't give you those hooks. But if you use one of the ODE solvers directly, then you can hook into it and you can limit values artificially, or you can create all kinds of weirdness if you want to. But yeah. So that's how to do it at every time step. So you can say, it follows this, and then if it goes above this point, you can even have if statements in there. If it goes above this point, then it's always this value or whatever. So yeah. So that's how to do it in your model when you're doing your simulation. I would like to get. I mean, ideally, I would do an example for you. I wish I had time to do an example.
I think I actually have some saved from the prior MATLAB class. This ODE stuff, I can probably figure it out.
Yeah, I mean, setting those up. There's lots of stuff on setting them up. Just like as ODE solving, like that's pretty straightforward to do. And I'm sure you can find an example of using state space in an ODE solver. But I don't know, and also you got to be able to turn a transfer function into that too, which is, we've talked about that in systems and whatnot, how to do that. How to turn it into a differential equation, from a transfer function to a differential equation. And then from a differential equation, you can go to a what is essentially a state space model, which is required for ODE45, which is a system of first order ODEs that are coupled, right? So if it's like a 4th order single ODE, you can break that down into 4 coupled first order ODEs. And that is something that they talk about in the MATLAB documentation. You can look at it online. There's lots of stuff on that. But the limiting of your input of your control effort in your simulation, that's something that I know that people do it all the time, but I haven't seen a lot of stuff out there on it. I had to do it, and I just that was how I went about doing it. There may be a better way to do it, but I mean, to my understanding, that's the easiest way to go about it. So there may be other methods, but actually using the ODE solvers is the one that I found it to be pretty straightforward. It is a little bit of work to get it set up, but once it's set up, it's not bad. It's pretty intuitive. I mean, as intuitive as anything is in MATLAB. So. Very intuitive. 2 thumbs up. Okay, so we are going to embark on essentially this one controller design method. Wish I could make this smaller, but I can't, so I won't. All right, so we will consider single input, single output control plants. It can be written with input U, state vector X, output Y, state model matrices A, B, C, and D, and these is our state and output equations. So, unfortunately, even this is single input, single output. So, I mean, it would be nice if our time would allow us to do multiple input, multiple output. But for now, we're just going to do a single input, single output, but we are doing state space model instead of a transfer function model. So at least doing that. Plants of this form can be written in the block diagram form shown in figure 9.1, which is here. So if you have an input coming in, it goes through this internal state, and it comes out as an output, right? So input to output. Essentially, all this is those two, the state and the output equation, written as in block diagram form. So y equals the sum of cx plus du, that's the output equation, x dot equals the sum of ax plus bu. So those are the two formulas. And then the relationship between x dot and x is one of integration. So you integrate x dot to get x, and that's the block diagram representation of it. The reason that we show this block diagram representation is that we are going to do state feedback. That's the type of controller design we're going to do. So we're going to feed back not the output, but the state vector. We're going to take the state vector out, and we're going to multiply it by these gains that we're going to compute, the gains of the controller, and we're going to bring it back to a summing junction and compare it to our command, which we'll talk about a little bit how that works. But the idea is that we know all of our states. Like we have a measurement, you could say, of all of our states. That's one way to think about it, is having a measurement. I mean, we're assuming we know them perfectly, and it's not just an imprecise measurement. We assume we know all of the states perfectly well, and we can use that knowledge to decide what the gains are going to be. That is the ideal situation whenever you have any feedback system. You know all the internal states, and nothing is a mystery. You know them all perfectly well. But real systems, real control systems, we actually have to measure things, and we often don't know all the internal states. We only know maybe like 1 or 2 or 3 outputs, and they might not all be related to states directly. Maybe they're just like some aspects of the states, but maybe some subset of the states. So ideally we know all the internal states, but we might not. And we're not going to consider that in this class, not knowing all the internal states. We're going to assume that you know all of them. This actually, this introduction gives you the stepping stones to do the next level of output feedback, but this is the easier one. So we'll go with this first. Okay. Plants of this form, okay, we did that. Let us consider the following feedback control method called state feedback control. We will feedback the state vector x, operate on it with a 1 by n vector of gains k, and subtract the result from the command r, the result of which becomes the input u, as shown in figure 9.2. And so that's what we looked at before. You feed the states back, and you compare it to the command, and you use that difference as the input to the plant. So instead of our controller being in the forward path, the cascade compensator, like we've done in the past, right? All of our previous compensators showed up. Our control loop looked like command, summing junction, controller, and then plant, and then output, and then it was just unity feedback, right? That's what our controller loops always used to look like. Now we've got non-unity feedback, first of all, but we're putting not just any old transfer function there. That's our gain transfer function. So we're putting in a vector of gains in that feedback loop. And that's where all of the control happens. So we don't have a controller here at all anymore. It's just the gains that go back through here. All right. So that's how this compares to what we've been doing. Good. The control problem for state feedback control is to determine the n gains in K such that the closed loop poles are located in desirable positions. The gain n, which is a real number, it's just a constant, is provided for steady-state error considerations, which will be addressed in the next subsection. A new state model can be derived for the closed-loop system as follows. Okay. Let us consider the command R to be our new input, okay, instead of U, which is now the control effort. So U, so this was, remember, this is the dynamics of our plant, right? What we're looking for now is the dynamics of the closed loop system. And so we have a new model to consider. So the input to our plant is no longer our input to the system. Our input to the system now is our command, right? We pull it back a level. So it's just like in our project where the motor voltage is the input to that electromechanical system, right? Like that's the voltage that drives the whole system. But we want to do control. We don't want to set that voltage. What we want to do is we want to set the position of something. So our command is going to be a position, and the voltage is going to be whatever the controller says it's going to be. And so our new input to the system is our command value. Same here. So let us consider the command to be our new input instead of U, which is now the control effort. So U is the control effort, is the amount of effort that has to come into the system from outside. So in our project, it's the voltage, right? What is the voltage that you need to provide? And when we were doing simulations, that's one of the things that we had to look at is, in order to control this in this way, what voltage am I assuming I'm applying, right? Like if I'm assuming I'm applying 10,000 volts, probably not realistic, right? So I can only supply so much voltage. It's only something that is it's inconsequential. It's all internal until it matters because you can't supply enough of it. That's when it becomes important to know. So we do need to monitor it. From the block diagram, we stuck n here in here as this gain in the command. So let's consider the command R to be our new input. So from the block diagram, U is equal to nr minus kx. And that's just found by reading off from this diagram. U is equal to nr minus kx, which can be substituted into equation 9.1 to define the new state model. So our equation was x dot equals ax plus bu, and y equals cx plus du, our usual representation. Now it's x dot equals a minus bk x plus nbr, and y is equal to c minus dkx plus nbr. The eigenvalues of a minus bk, which can be found from equating 0 and the closed loop characteristic polynomial, which is the determinant of SI minus the A matrix, right, which is A minus BK, the new A matrix, A prime, if you will. So it's the determinant of SI minus that, are equal to, so the eigenvalues of this can be found by equating this to the closed loop equal to 0, and the characteristic closed loop polynomial are equal to the closed loop poles, which we would like to place in specific locations, right? That's our goal, right? So we closed the loop and we found how the system behaves now with this new input. Notice that our input changed. Our input was U before, but now our inputs are. And our A matrix was A before, and now it's A minus BK. So we've got some things that have changed. And now what we want to do is we want for these closed loop poles to show up wherever we want them to be. And we can just try to choose K to make that happen, right? Those closed loop poles, their location is dependent on this polynomial, and it has K in it, fortunately, because, you know, if you're going to vary something and it doesn't depend on that thing, then you're up a creek without a paddle, as they say. So, those specific locations of those closed loop poles that we're aiming for can be specified by the design characteristic polynomial, PD. So PK is the closed loop characteristic polynomial. The design characteristic polynomial is PD. PK depends on the n gains Ki, and n equations can be found by equating the polynomial coefficients of PK and PD. So we say, where do we want those poles to be? We'll build so once we specify where they are, those closed loop, we build where they are. If we set that into a polynomial form, we build a polynomial out of that, it's going to have n coefficients, the order of that system. And we're going to set that equal to the actual closed loop characteristic polynomial. So we set those two equal to each other and we solve for all the gains that have to make that happen. Does that kind of make sense? I don't know if that's clear. So for instance, say you had a second order system, okay? And you wanted your closed loop poles to be at like s plus 2 and s plus 4. So minus 2 and minus 4 on the real axis. Those are where you wanted them to be. So your PK would have to be equal to this. So this is our PD. It's our design. This is what we want. Our PK is going to be equal to whatever it is. It's going to be a second order polynomial. Our PD is going to be s squared plus 6s plus 8, right? Our PK, we compute it. It's going to depend on all of those gains. It's going to depend on two gains in this case, a K1 and a K2. And we're going to be able to set the coefficients of this polynomial equal to the coefficients of the other polynomial and solve for what gains we have to make the closed loop polynomial this design polynomial. We want it to be that design polynomial. So that's the plan. Solving for
what are the coefficients again? You said. What do those represent?
So our closed loop characteristic polynomial, this one represents the actual closed loop pole locations, right? And it depends on the gains. This is our design. This is what we want. We set these two equal to each other and solve for what the k's have to be equal to this, to make PK equal to PD.
And why would you choose 2 and 4? Is that just
If that was your, so if you wanted an overdamped system, I mean, for instance, that's one way. If you wanted an overdamped system, you might want your poles to be there, but probably you would want something other than that. I mean,
just an example?
It's just an example. I just chose them because they were easy to multiply. I didn't want to multiply complex numbers, so I just left them off. But they could be complex, right? I mean, you could put our closed loop poles anywhere in the complex plane. So, but suffice it to say, it always comes out to a real polynomial, and that real polynomial can be solved for what those gains need to be. So and it essentially just comes down to solving an algebraic problem of equating coefficients. Two polynomials you want to be equal with variable coefficients, so you have to set all the coefficients. So the s squared coefficient on the design polynomial has to be equal to the s squared coefficient in the closed loop characteristic polynomial, and then et cetera, et cetera. You have to equate all of the coefficients for each order. So it's straightforward, but it can be very tedious in the general case. Let the coefficients of PD be delta I, and those of PK be denoted kappa I. Okay. So the design ones have deltas, and the K ones have kappas. Then the n by 1 vector containing kappa I can be expressed as a linear combination of Ki as follows. So kappa is a vector that contains a linear combination of these gains. So where script k is an n by n matrix of coefficients that were derived from A and B. So I'm just saying it's going to be of this form, right? Kappa is all of these pk. So this is going to be some polynomial with these polynomial coefficients, and I'm representing those by this vector kappa. And this script k is, it's something. It's something for a given problem, for given A matrix, B matrix, it's going to have a certain form, but I'm not going to say what that is right now. I'm just going to say it's something. Let delta, the argument requires this for now. Let delta be the n by 1 vector of components delta I. So these are the design ones. These are the coefficients that we want, right? Since the vector delta is specified by our design requirements, we can solve for k as follows. We know that kappa is supposed to equal delta, right? That's what we want. The design coefficients to equal the actual coefficients, okay? And therefore, we can say, okay, we'll just stick 9.6 into 9.5, so we'll just say kappa is equal to delta, which we know. So we'll plug delta in up here for kappa, and we get this expression, where we've switched the left and the right-hand sides. So script k times k, because t is transpose. I'm sure everyone recognized that. I just was assuming. Equals delta. And you guys are thinking, oh shit, linear algebra again, right? Yes, linear algebra again. You thought you were done with that with me, because I know that I made you guys love it when you were in my systems class. But now even more linear algebra, you thought, because we were just doing a single input, single output, transfer functions and all that. No more of this. But here we are with transposes and inverses. Oh no. That's it. Okay, so we want to solve this. We want to solve this for the gains, right? Ideally, we know what the gains are. So we just want to solve it for the gains. So if we left multiply both sides by script k inverse, then we get that, right? The next line. And then that last line, 9.7, is what we get if we take the transpose of both sides. And that little m hat is because for some reason some of the parentheses don't come through in Illustrator. I don't know why, and it drives me crazy. So we've solved for what the gains are, as long as we can figure out what the hell this script k is. We know, and we're good, right? Equation 9.7 is valid for all cases in which script k is invertible. Okay, so footnote. We leave the following as an open question. Under what conditions is k invertible? Okay, so this is fun. So you guys know you're getting to the point of, some of you are in this as a graduate class, some of you are seniors and you're about to be graduate students, and some of you are not going to go to graduate school next. But suffice it to say, this is a preview of the type of shit that you have to put up with in graduate school, where they leave it as an exercise for you to think this out. So, anyways, 9.7 works as long as you can invert k, right? So that's good. However, there's a special form of the original state space model that always yields a simple solution for k. Okay? The phase variable canonical form. So, this is the part of the lecture where we're going to have a little break and we're going to go to this appendix for a moment. Let me take a look. I don't know if I sent it to you guys. I might have forgotten to. AC. What was the appendix? B21. B21. Crap. I hit the wrong button. Aha! You thought this lecture was only 7 pages, but it's actually like 20 pages.
Typical.
It's like a homework problem.
It's only 7 questions until you look at question 1. It says refer to questions 1 through 10.
Yes. First, solve chapters 4 through 6 questions.
And use the answers to all of those questions.
So what we're saying is, oh, okay, this script k that shows up in our gain solution is best paired with the canonical form that we're going to represent here. And I'm going to I should split this lecture here because I don't want to make this one massive thing. What? I'm recording right now. How do I not have a button to stop? This is